We good.
All right, we are just about at time. So welcome to the Systems and Infrastructure track here at SCaLE. We are here welcoming Justin Garrison from Sodero Labs to talk about the Immutable Linux, the state of Immutable Linux, as you can see. Couple notes, we are taking questions throughout the talk. Justin's comfortable doing that. So if you have a question, please raise your hand. I will try to run the microphone back to you. And there's props. There's cool props.
We're getting into it. Yeah,
Justin's going to have a good time. So let's give a very warm welcome to Justin.
Yeah. Everyone having a good scale? Might change now. So we have like, what, 25 people in here, which is about 24 more people than I expected. So thanks for coming. It's a Sunday morning. Yeah, I'm Justin. I do work at one of the vendors that create a immutable Linux distro, but this is not a thing for what we do. I put ours at the very end, so if I don't get to it, you know it's not a sales pitch. I'm going to just try to cover as much data and stuff about the other ones as possible. And while I try not to hold back my opinions about things, I've been doing this for a little while, I intend to throw no shade against any other projects or developers or maintainers about these things. Everyone builds their things in their own constraints, and they have their own ideas and their own tools, and that's how we get further in life in a lot of ways. So I've been using immutable Linux distros for, more than a decade. Yeah, so we're just going to kind of go through some of it and just talk about it. And the front line here, you might be in the splash zone, just FYI. I do have some props. So fair warning. So this is the thing that every marketing is like, we're immutable, so that's good, right? And it's just like, what is immutable? What do people expect from a distro that says it's immutable? Any guess? What would you say if someone says this is a mutable distro? What does that mean you can or cannot do? Read only, right? Like, you can't write it. You can't modify to it. You can't change the distro. And that should give you some assurances. There's some things about, if I can't write something to it, then a virus can't write to it, right? Like, that's kind of the goal here of what we're trying to do. And then also we have some assurance that the thing that we deployed in production is the thing that we built in CI/CD, something like that, right? So it's like, I can trust these things might be the same because it shouldn't change in production. It'd be mutable if I did that. And I'm here to tell you they're all lies. Unfortunately, Linux isn't designed to be immutable. It was never designed to start up and run and not change anything, right? Like, we have to put things in memory. We have to run things on CPUs. We put log files for debugging. Those are all mutations. Those are things that mutate the world. And so anytime someone says, we are 100% immutable, they are lying to you. They're trying to get you to a goal of, maybe this is better than what you used to do in most cases. And if we look at it in that framing of like, I used to go on every server and run yum updates and yum upgrade, and then I didn't know what happened. Like, if it broke, maybe it was in some state, but like, hopefully it got rid of the security, whatever. Like, that cycle is what this is mostly changing. The thing that we used to just like change the whole world in place is kind of what we're trying to get to here. So the immutability side of it is fungible. I mean, it's mutable, that definition, I'll say that. And also 10 years of working in big enterprises has taught me to hate slides. I absolutely hate making slides, mostly because every company that I worked at required lawyers to review my slides. So I'm sorry that these are like the lowest effort slides you're ever gonna get. And I try to do as much possible in live demos because, this is these are my design skills after 10 years in corporate America. Immutable distros need some way to run software and install software. And they all have different ways of doing that. If we're looking at strictly the server side of things, a lot of the world has settled on containers as being the thing, meaning specifically OCI, Docker containers, whether that's Kubernetes or whatever. You run a container, and that's the mutable bit. Like, you ship a tar file with lipstick to a server, and then it runs. And that's the thing that we're doing. But that's not limited to all immutable distros. Flatpak is coming around as a more people are aware of it. I was using Flatpak when it used to be called XDG app. If anyone remembers when engineers used to name things. It was called XDG app, now it's called Flatpak. This is what you're getting in more of the like desktop class, like, hey, I want to run a GUI app, like on a Bazzite Linux or like a Steam Deck or something, where it's more, I'd say, user-friendly, but it is solely focused on a UI that has a person clicking around. Do not try to run command line utilities from Flatpak. You will have a bad time. It's not designed for that. Snaps are exactly the opposite, where snaps were designed for services. For some reason, Ubuntu decided that they didn't like regular OCI containers. They wanted to own the stack, and they just kind of did their own thing. And Snap Classics really sucked, and they were invasive, and Snap new ones don't have as many features, and now they also run GUI apps. I have no idea what Ubuntu's doing with snaps, but it's really confusing as someone who has stopped using Ubuntu mainly because of their persistence on everything being a snap. And I did not like that, and I moved on, but you do you. App Image is actually one of my favorite portable packaging things. It's GUI focused. It's something that you would run on, again, I'm running uBlue or not Bazzite, man, what's it called now? Fedora Silverblue, Bluefin, that is the one. They're all the same. I'm running Bluefin on this laptop, and I like running app images. I also have Flatpaks. App images are basically like, what if we shipped you software in a CD, but that CD was digital? That's literally what it does, is it has like a loopback interface that mounts the software, and it uses Fuse to like, here you go, here's a CD, and now you can run software from it. And that's all it is, really. It's like a live CD. I like it just because of the portability. There's no daemon requirement. It's just portable, but it doesn't have all the integrations. Sometimes things break, like NVIDIA drivers. That's hard to package because there are things on the host that need to be in the application. Same thing for containers, Flatpaks, all that stuff. They all have those same problems. There are things on the host you need to match in your container. Brew has been one of my favorites as a long time. That's the most ridiculous, worst package manager I've ever seen in my life, to, oh my gosh, it has all the software. It has it up to date. For probably 5 years, the vast majority of my open source contributions was to put Linux packages into Brew. Because it's like, I want this tool, I'm going to put it in Homebrew so I can use it. And I converted some companies to do the same. I said, hey, you should package, like AWS, you should package this as a Brew. They said no, and I said, forget you, here you go. I did it myself. So there are things that I love about Brew. It is the best, worst packager I've ever used. It's all based in Ruby. It's getting faster, but it's still like, let's just duplicate Python 30 times on your file system. This is cheap. Before 2026, right? In the era when disk and RAM was cheap, this is fine. We can just duplicate all that every time, and you just have a whole file system for every package, and it's okay, right? There's not a lot of sharing there. But Brew's really easy. Systemd sysxt is, again, engineers naming things and putting sex in a command line tool and not even thinking twice about it. It's just, every time I look at it, I'm like, you can tell an engineer did this, and no marketing person ever read this as, let's go out with that, that's fine. These are system extensions, specifically for systemd. These are just like raw, like volumes, like snapshot a drive and like mount it anywhere on your file system, and like systemd will manage it. As someone who's carried a pager for a long time, that scares the hell out of me. That is one of those things I'm like, there again, you have to match things with what's on the host, what is in the kernel, what's in the application. Like, just take a raw volume and throw it anywhere you want, and then load libraries from it. Is really scary to me. But also, people do it, and it's working for some cases, and I get that. You have to have a lot of controls. It is just a flexible mount the volume and have fun. You need to set up your own process and utilities to test and make sure that that thing is a little more aligned, unlike Flatpaks and Brew and those sorts of things that kind of give you some of those nice additives to make sure that something is working before you try to run it. I'm just going to go over a few questions on each of the distros I'm going to cover, just to give you a little bit of background about like who owns it. That is important. What does it use under the hood to be immutable, quote unquote? Where do you put your customizations, and then kind of just how do you maintain something that's long term? Because you can read the spec sheet and say, cool, it's immutable, and then at the end of the day, you're like, actually, this kind of sucks. I will also say that if you're looking for an immutable distro, and you already have like a vendor ecosystem, pick that vendor's immutable distro first. Don't try to shoehorn someone else's immutable distro because you like it more. A lot of them have different technologies. A lot of them do it in different ways. But if you're trying to put flat car into a RHEL ecosystem, you're going to have a bad time. It's like you're going to have to do more work. You're going to have to integrate it more. So just FYI, if you want to save some time and you're like, this is going to solve my problems, just stick with the one your vendor makes. As someone who makes a third-party agnostic vendor version of this, I still recommend people try the immutable distro that their vendor ships first and see if they like it, see if they have problems, see if there's gaps. So I'm going to start with CoreOS. CoreOS was like the OG of immutable Linux distros. Anyone here have Android phones? Anyone use Chromebooks? It's all based on, like, CoreOS was based on that technology. And also, unfortunately, CoreOS was renamed to Container Linux, and then CoreOS, the company, got bought by Red Hat, and then it was forked and called Flatcar Container Linux by IBM. Because Flatcar also got bought by Microsoft, that's Microsoft. Anyway, it's a long history of, it's kind of the same thing. It's basically an Android phone for your server. Let me just show you what it looks like. And this crashed my terminal so many times this last week. We'll see how this works. That car start. I am just running a VM on my machine with each of these distros. Scoot forward if you can't see it because I don't want to make it any bigger. Let's go flat car, SSH. So I am now inside of a CoreOS machine, a flat car machine. The technology behind flat car is something called Nebraska protocol, which is XML. Don't look at it. Don't try to do anything with it. It is like, you can tell how old these things are because this is just legitimate, like XML sending back and forth. And they do one really cool thing where the AB updates have like binary diffs from one version to another. So instead of saying, here, get the whole file system and do an update, it's like, oh, I know the block sections that you need different to do an update. If you've ever seen one of my talks, I like to do props. So I think of a partition like a big bucket of stuff, right? So we have a bucket of stuff, and this is my 3D printer trash, which I kind of equate to a Linux distro. It's basically hopes and dreams that you throw on the file system, and you say, there we go, we're going to boot that. That is now our Linux distro, and we're ready to go. The thing that, sorry, I need another bucket. The thing that Flatcar and originally CoreOS does is they have two partitions. They're like, you know what would be cool if we could have twice as much trash. And they just say, hey, actually, the second partition here, I don't want it to fall. We're going to, while we're running from this first one, we just throw all our trash on the second one, and then when we reboot, we tell Grub to boot that one. And that's it. And that's all we have to do. We say, look, we have AB partitions, and we can boot from one to another, and they're immutable. Not really. But that's not the whole file system of your computer. Like, there actually is, what if I have changes? What if I want to do things? What if I have container images I pull down? I don't want to pull them down every time I reboot. I need some shared space of storage that is going to like always retain those containers. So there is other partitions that will still mount, like var and whatnot, that has variable information. Those will be separate from these two AB partitions. But Flatcar is that. It is two partitions that we put stuff into. And if I do, you know what, I have, I wrote myself notes because, of course. Oh, I don't have, what? I also don't use this laptop very much. What is the command? Here it is, ls. So if we look at this, we will see a user A and a user B. Literally two buckets on the file system. That is it. There are two drives that we just throw everything into. They're both about a gig. And then they have these other weird things like OEM and OEM config. A bunch of other distros started copying this where I think CoreOS thought that like every vendor was going to go this route. And so they're like, let's just make an OEM area where they can customize whatever they want. And if you run in AWS or you run somewhere, this is where like your customizations for that environment go. They all go into OEM, and it's like your scripts to bootstrap and start it. CoreOS also heavily relied on cloud inits. Everyone know cloud inits? It's like the world's worst config management. Like Ubuntu wanted their own config management, and at the time it was Puppet and Chef and Salt, all these really cool advanced systems that can do a bunch of stuff. And they're like, what if we just ran Python with a bash script? It's like, well, and you could just run it every time, and it would just reconfigure the node every time. I'm like, well, like, does that work everywhere? Like, I don't know. CoreOS went that route and said, yeah, absolutely, we're going to go that route because we think that the cloud and VMs are the future. So every time the machine starts, it looks for user data and cloud inits, and it runs that. And then it just does this A/B partition. But like I said, immutable distros can't write to it, right? Hello. Oh, I need to. It works. It's not immutable. There's nothing about that that's immutable. I can even sudo, I think they have it. Let's see. Let's go in and change something. Fail. It works. This is not immutable. Like, what is going on here? Like, why did they say this is a immutable distro when I can obviously mutate some core files in the file system that I shouldn't be able to? And the reason for that is this magical thing called overlays. I'm going to move these. And let's say I have Etsy Nginx, all right? This is my, oh, geez, I made a mess of it. Get out of here. Let's say I have Etsy Nginx, and I need to put my hello file. And I want it in the Etsy directory. How would I get it there? It's immutable. You can't, right? Overlays are this like fancy trick where we just like pretend that literally overlays one file system, and then we're like, boop, look it, we win. We can put one file system. I mean, so literally it just layers one thing over another, and then the view you see is, I have all my files. All my files exist because that got shoved into some weird place that's an overlay, and we can see it. Where? There's my overlay. I'm going to make that a little bit smaller so it doesn't. There's these things called a lower dir and an upper dir. That is, the lower dir is the immutable parts. The upper dir is you made changes. And so we can go find it. And we can go ls sysroot. No, sorry. I gotta make it smaller. There, sysroot Etsy work. That's where it is. It's really funny because your upper dir goes into like a temporary work folder first. Like it goes in sysroot. It goes like lower. It doesn't never touches lower, but it goes in Etsy work, and then it goes into your upper. So it's really fun to try to like troubleshoot these things. If I look at, yeah, there's. Where is my sysroot? You gotta trust me on this. I did it last night. Sysroot pivots to root, and then it's user share flat car. You know what it is? Oh. It's hidden. It's a hidden. There it is. Etsy work. Dot. And then you get this weird work. Is it a RAM disk? No, it's a partition. It stays. It's literally mutable. Like it will write to a partition. If I parse this output somewhere in mount, I can find where that's actually mounting it. But yes, absolutely. I'll repeat. Yeah, it does persist across the boots because it's on your file system. When I looked at that, what was it? LS block. There is the OEM config. There's my root VDA 9. Will have some overlay in there. So those folders end up showing up in this root. So you're still mutating the whole thing. Like there are sections that you can't touch that don't have an overlay. But in general, they put down, here's our file system. You can do whatever you want on top. And then whenever you do an upgrade, we're going to take your bucket of trash. And then your view of it is just like, here's your overlay. very nicely right there. And that's it. That's what you see when you run the system. So you still have all the changes you make. You still have a home directory. You still have stuff that you need to configure. Everything is still there. And so it feels like, the way I always describe CoreOS or Flatcar is it is just a Linux distro without a package manager. It's not really immutable. It's just like, well, what if we just don't have apt? And it's like, oh, we run containers, so it's good. I love CoreOS and Flatcar. I ran it back in the day. The thing that CoreOS was trying to do, which is like their goal as a company was to secure the internet. So they always said over and over again. And by trying to secure the internet, they said the things we needed was an OS that automatically updates. And that was it. It was just, and how they got there was they needed to make updates more secure, more stable. So they said, actually, we need to make this overlay file system so we can always write the underlying file system. And they built a distributed database because they said, we need to cluster machines. We need 5 machines together to only reboot one at a time. And that was how they were going to get there. To secure the internet, they built those 2 core technologies of we need to just make updates easier in general across a fleet of machines. And that's kind of how we got to Flatcar Linux. It didn't do anything else. And again, it stole it from Chrome OS. Chrome OS was doing this at a large scale already. And they said, well, we just do it on servers. And they took all the technologies and they did that. I don't think I have another note. Oh, and update engine. This is how you update it. Sudo update engine client, I think. Client update. If you, in 2026, are writing command line like utilities with underscores in the name, you're a cop. Like, I'm sorry. Like, this is like, don't do that. Like, but like, I know this has been around for a minute, so I don't even know if I have internet. But anyway, that's like the update is just literally you're gonna go A partition, B partition, back and forth, and you have 2, and you just throw away one when you're gonna write the other, and that's all you're doing, and you're giving those overlays to give files that you want to change. That's the whole basis of Flatcar Linux. Kairos, that's the next one. So Kairos does things a little bit differently. See if my terminal crashes. Every time I would start one of these VMs, it would crash. Wait for it to start. Oh, I forgot one thing with Flatcar. Customizing Flatcar. So we have our cloud init, which will start, like, initialize or customize the system when it's booting. That's not enough. They created a thing called ignition because they realized that systemd, when it starts, assumes the file system is in place and assumes the files for services are there. And so a lot of people for a long time in their cloud inits would like write a file, reread the file system from systemd, start a service. And it was really hacky back and forth, and some things didn't work that way. But also, what if you need to partition a drive? What if you need to actually lay out a file system of some sorts? So they wrote ignition, which is it's basically the same thing that runs in your initramfs. We have to explain what initramfs is, right? When a computer boots, the BIOS or UEFI initializes the hardware, goes over to the bootloader. The bootloader reads the kernel and initramfs. These are supposed to be, the kernel is how to initialize the hardware. Initramfs is a tiny piece of RAM that initializes that file system so it can start running the real system. Initramfs mounts a bunch of stuff and then pivots to the real file system. That's how the process works. So what they decided was, actually, in that little initial, before the machine fully boots, we get PID 1, we can do a bunch of stuff to the hard drive. We can format things, we can drop files, we can do all this stuff because the OS doesn't think, it's not fully available yet. The kernel has not started, PID 1 has not started. So they give you this little shim of JSON that you shove in place, and it kind of looks like cloud inits, that just like, hey, let's just do a bunch of stuff to the drive before it starts. And that's a thing that Flatcar and CoreOS did later, but that's how they kind of initialize bare metal servers, that like, oh, I don't have user data, I need to format stuff. A lot of other distros, again, use that same sort of pattern. So I'm on a Kairos box now. And Kairos is a meta Linux distro, similar to how Bluefin is a meta. It's not the actual distro. Kairos takes another distro and immutabilizes it. It says, oh, do you want Ubuntu? Do you want, I guess you wouldn't take a Core OS, but you want Red Hat? You take another distro, and then we're going to wrap it in immutableness and then deliver that to you. Mainly for like compliance and onboarding, because training people is hard. And if you tell someone they don't have Ubuntu anymore, if they're used to it, they're like, oh, well, now what do I do, right? Like, that's the hard part of moving forward with things. So they kind of took this approach of, what if we took the other distro and repackaged it as something that was immutable? And if and one of the things they did was they packaged that distro as a container image. Again, it's a tar file with lipstick. Okay, this is all it is. And so if I look at my image, this one's a Ubuntu. And then if I go over here and I don't know if I put it in my notes. No, of course not. Oh, was it? Thank you. I still didn't put it in my notes. No, it's crane, export, image, tar T, I think. This will download that container and show me what's in it. It's just a file system. It's this. It's just the trash. They just shoved it in a container image, and what they do to make it run is they repackage this as this. Literally. Like in the technology, it mounts as an IMG file, which runs as a loopback, which is a CD image on the disk. And so instead of having 2 buckets, Kairos doesn't need to do 2 buckets, they have 2 CDs on their disk. They just say, actually, I can just have this. I can go A, B, back and forth. And I don't need to have 2 full partitions. So if I look at my partitions, I don't have the user A, user B. I do have other partitions because, again, file systems are fun, and we have to put things in different places. But I don't have to do a full partition for one and change the boot. The bootloader is just changing which image it mounts as loopback and not what partition it boots from. And I know I wrote this in my notes. Yeah. Init ran. Nope. Oh, it's squash. It says I should have a code. I probably messed up all of my notes on this. Let me try one more time. Hello setup. Sudo. Oh, what am I doing? Setup. There you go. This shows me where I'm running from. I have a live directory, and that is like my squash FS that it's running, that it's mounting. That's what Kairos is doing. It just says instead of partitions, we're going to do it from ISOs so that it's easier to package anything into the ISO. And those ISOs get distributed as container images. It's just a bunch of tools that we glue together in certain ways. And again, this is supposed to protect the writability. Does anyone know why this CD is illegal in the US now? Not because of Ricky Martin's good looks. This one has a rootkit on it. Y'all remember Sony back in their infinite wisdom decided that we didn't want people to copy our CDs, and so they wrote a rootkit and put it on this CD, so if you loaded it into a Windows machine, you couldn't copy the songs off of it. It would actually hide the CD from you. This is exactly the type of stuff that a mutable Linux distro should protect against. Obviously, this wouldn't run on a Linux distro, but if I try to do touch Etsy, hello, I always got to do it, I can still write to this file system. I still can write to this distro. There's nothing that's stopping me. It does the exact same thing that Flatcar's doing with an overlay. It stores it in a different path under a different name, but it's the same thing. There's my overlay. I can see my, I have an upper dir and run overlay fs. I bet if I look in my Etsy, there's my hello file. And it just merges that into Etsy when I ls Etsy to say, okay, where is this thing at? So there are changes I'm still able to make. This is not what we think of as I can't change it in Immutable. This is, we're going to play some tricks to make it work because Linux was never intended to be fully immutable. There are things that all these distros are making changes for and doing. I don't think they also do ignition, user data, and system extensions. Exact same thing as Flatcar. It's exact same technologies to kind of customize it during initialization. Again, it's just taking Ubuntu and then how would I package Ubuntu in a mutable way and then allow people to extend it. Both of these distros, if you want to run things like NVIDIA cards, NVIDIA GPUs, you have to go get a bunch of system extensions and mount them on the file system, or you get a flavor of the distro that has some of that built in already. These are things that are really invasive to the file system, and the kernel needs them really early in boot to be able to load kernel modules. That's all different things that you're going to have to do with any of these sorts of distros. Thankfully, they don't have underscores. Oh, you know what? That's why I didn't see the file system. I booted the wrong VM. This is actually running from the live host. I'm going to hurry up because I know I'm going to run out of time. Nope. Most of these distros will run in a live state from a live CD, and when you install them is actually when they give you all the overlays and things that you might expect. I'm not going to wait for it. Just kill it. What's our next distro? Bottle Rocket. Anyone running Bottle Rocket? I'm sorry. I'm not actually going to cover Bottle Rocket because you can't run it outside of AWS or technically a version of vSphere. But Bottle Rocket was intended to be Amazon's immutable container Linux, and it only runs inside of AWS. I was at Amazon when we launched it. I had a lot of opinions about how we were doing things. They basically do the two-bucket approach for things, but the thing that they wanted to do is they said, hey, guess what? No SSH and an API for configuration. Those are both lies. The API for configuration is actually just a customized version of Cloud Init. It literally is just like, hey, we don't take regular Cloud Inits. We wrote our own because it's Rust. Yay. And so we have our own configuration in TOML that you mount into the file system, and that does your configuration. They don't have like an early ignition stage of doing things. They assume it's always going to run in AWS, and so everything can be done from the metadata endpoints that AWS provides and pull in from their customized version of Cloud Inits. No SSH is, again, it's not on by default because you have to enable an admin container, but they run a proprietary SSH called Session Manager. Back in the day, I was actually a big fan of Session Manager. I thought it was cool because it was SSH over HTTP. I'm like, that could be neat. But also, it's proprietary. You can't do anything with it because they run the backend services for it. So you can't use it anywhere else. If you want to SSM to servers in your host or like in your data center, you have to connect them to AWS, and you go through AWS IAM and then back down to your server. It's kind of a pain. So Bottle Rocket, in general, they only have the APIs available that their Cloud Init does. It only runs in AWS. They will push it on you as the default container OS you should use everywhere. FYI, it'll come. I don't know if it's default now, but it will come. There's a lot more and more things that are making it the defaults. It does not have, there was promises originally about lower resource utilization and a lot of other things. Most of those things ended up being false because when you don't have shared libraries and everything's statically compiled in Rust, guess what? You use more RAM. There's a lot of things that happen in a Bottle Rocket OS that I'm not going to go into all the details, but those are just some things you should be aware of If anyone tells you run BottleRocket in GCP or something, just walk away. Like, it's not happening. I worked on EKS Anywhere, and we tried to get BottleRocket into data centers. We made one version for VMware, and we had one customer sign up for it, and now we have to support it, or they have to support it. I don't know there. But that's basically it. They only want it for AWS. If you're in AWS and you're running containers, they want you to use BottleRocket. It's only for ECS and EKS, nothing else. So just a heads up on that one. Hey, we're to the new CoreOS. So the old CoreOS, like I said, the company got bought by Red Hat. Red Hat had a thing called Project Atomic. Did anyone use Project Atomic back in the day? Yes. This was exactly the same time that XDG app was still a thing. I was back in the day in IRC with a bunch of the Red Hat engineers, and they told me they had this really cool thing. It's called OS Tree. I'm like, what is that? And they're like, it's like Git for your file system. I'm like, that sounds terrible. you know how good I am at Git? Not that great. And so you're going to do that in the whole file system? No thanks. But then they also did something that made me completely walk away from it, where they said, what if you could still install RPMs? And I'm like, you don't get it. Like, that's not at all what I want to do, the exact opposite thing. And they said, but RPM OS Tree gives us this overlay, but we love writing spec files, so we can still distribute RPMs. I'm like, I hate spec files. Don't make me do that. And that's when I stopped paying attention. Now I'm running it. So Fedora CoreOS, again, it went through this whole like weird naming convention thing. When Red Hat bought CoreOS, they just said, CoreOS is really popular. We're going to use that name instead of Atomic. And so they just rebranded Atomic to CoreOS and changed almost nothing. They took some pieces like Ignition and a few other things that they liked, but the base of the file system, how the file system and how the actual OS works is exactly the same as what it was in the Atomic days. So if you're used to that, it'll be the same. Oh, and also getting to boot C. Anyone heard about boot C? It's a build tool. It's just a build tool. It doesn't change anything on the OS itself, right? Kairos packages their distro, like I showed you, as a giant tar file. Boot C just does the same thing. It's just, hey, what if we had our own build packaging system? They mostly did that because the RPM or the OS tree tools for building a file system really sucked. If you ever had to build a file system and distribute that file system with OS tree, you had to learn an entirely different like language, and it was just like, we're just like putting Git repos up on a web server, and then this thing's pulling down files that it wants. It was really bad. And so they said, actually, all of that nonsense of OS tree sucked, so we're going to redo it all as containers, and we call it boot C now. Boot C from the clients isn't different. It's still OS tree under the hood. You have a boot C command, but it's the same thing that we had with OS tree before. It's just the building and distribution has changed. So if anyone tells you like boot C is better than OS tree, again, run. Oops. So let's look at it. This one, FCOS, I also hate as a name. Just because, I don't know, it seems like it would be something else. Let's get into it. They also have, in Red Hat's infinite wisdom, Ignition is cool, but it's JSON. And for some reason, Red Hat engineers are allergic to JSON. So they wrote a tool called Butane. You can write your Ignition as YAML. And then you convert it into JSON. And then run it the same place. Why does Butane exist? I don't know. If someone knows, please tell me. But it pains me so much that they don't like you writing the JSON. They're like, no, you have to compile it from Butane first. Compile your Butane, make it Ignition, and then boot your server. I'm like, stop it. Just we don't need more tools than this. All right, we're in. Something that OS tree and again, I hate calling it Fedora CoreOS. I don't know why. I always call it OS tree. I use it on my laptop, but the thing that they do, everything is here you'll see is like symlinks. Like we're just symlinking all over the place. We're like, what if we just had more symlinks on the file system because everyone likes reading those and following them. So let's follow one. This OS tree looks interesting. Let's get it up top. OS tree. Okay, so we got boot 1, boot 1, 1, and deploy. Let's go into deploy. Oh yeah, of course. Gotta have the name in there. Backing, I think that's the one. Nope. Everything is SHAs. That's usable. So this is the first distro that I would say like becomes not for human consumption. This is when you're like, okay, I have to know these SHAs, I have to follow these artifacts. They literally like recreate an object storage on your file system. Right? Just like Git, right? We have, if you ever try to like scale S3, you have to like take the first 2 characters of the SHA and like make a bunch of directories like that so it's evenly spread, and they do that on your file system. And I'm like, this sounds crazy. Engineers love it, right? Like engineers are like, oh, we get to do all this cool stuff that we couldn't do in the cloud, and now we do it on the file system. Why is that still? Oh, it's trying to update on me. Thanks. Please don't. SCOS notes. Of course, see, I called it Fedora Core OS. I have to remember where those objects are. Here. That's your file system. Have fun. Like that's how we separate it out. That's how we split it out. That's how we make sure it's balanced. And I'm like, you don't need to do that on a hard drive, but I get it. Like engineers love engineering. But we can trace that down. So if I go to boot C status, of course. Oh. The thing that's interesting about boot C is I'm not limited to 2. What if I wanted 10? It's a bad idea. But if the whole thing is just symlinks, I don't care what the partition layout is. Again, in boot C is another one. There's one partition for this that we're just swapping back and forth those boot.1 directories. So your grub, your SD boot, whatever is like, oh, I'm just going to go one or the other, and then we're going to follow the tree to make all the files, right? And we're going to figure it out. But it's mainly for computers to consume this. Don't try to do it yourself. And so I can see my commit here. I can see my SHA. I could follow that all if I wanted to. I'm running out of a little bit of time, so I'm just going to skip a little bit on this. Again, boot C. If it's a container file, you're a cop. I don't make the rules. So if I do crane again, crane export, look at, we made a container that's a file system. Isn't that cool? No, because it's just a tar, and it looks uglier. Because we have all those SHAs that are all those symlinks that we put everything in here. Again, not for human consumption. They even went as far as, you see these files xadder links? That's kind of weird. They separate out the file data from the attributes on the disk. Who does that? That seems crazy. So they actually split, like, hey, what if we had the same file multiple times, because we can have 10 boot directories if we wanted to. We want one attribute file, so we make sure that it's always the same. Partially because of SE Linux, but also partially because they're masochists. And so they actually separate out these 2 things where you say, actually, when I want to ls a file, I have to look at both those things. I have to look at the data, and I have to look at the attributes. And they split that out on the file system in OS tree. Does this sound like something you want to be on call for? It scares me. I run it on multiple systems, but I don't have to be woken up in the middle of the night and try to debug this. Like the distribution mechanism of it's in a container is neat. The fact that I can build it in a container file, that's kind of neat. All the other stuff is a little bit scary to me, and it sounds a little bit like, I think my next one. Oh no, I gotta skip one. It sounds like Nix. So we'll get to Nix in just a second. But I'm gonna go to micro OS. Again, I'm gonna go a little bit faster here. I'm sorry. I'm around too, so you can ask questions if we meet up. Let's stop this one. Is anyone using micro OS? Hey, sweet. So I can talk about it. Wait, I'm gonna start it down here. I hate the ooze. Micros start. There we go. Micro OS SSH. It'll come up. So the interesting thing about micro OS is to say, what if all of that complexity was just in the file system? We have cool file systems that can do this type of stuff. We don't actually need to make the symlinks and all of the stuff everywhere. We can make it look like a regular file system. That's mostly right. Even if I get a couple symlinks in there, that mostly looks correct. Like there's nothing about this that scares me yet. And I can spell snapshots. Snapshots. This is, oh, and I also forgot on Fedora Core OS, yes, you can touch Etsy. It has an overlay. It does the same sort of stuff, so it's not immutable. This microOS does everything in Btrfs. What if we had Btrfs snapshots for all of this nonsense, all of the symlinks, all of that stuff? What if we just made snapshots in Btrfs? And so anytime that I got sudo touch, it works. It's still going to work. Where does that go? In this case, Btrfs just says, I'll make you a new snapshot. That's really cool, because Btrfs just hides all the details as long as you want to learn Btrfs, which I do think it's a cool file system. I think it's very powerful. I think it can break in certain ways if you're trying to use too many things. But as a package component of this, I think it's a great way to implement this stuff. I really like how that works. The thing that I don't like is, again, I have to remember how this works. There's my snapper list. So I have snapper list, shows me all of those snapshots, and then my Btrfs subvolumes. Is that it? No. List, of course. Did I spell it wrong? Subvolume. Thank you. Snapshots for all those things. You'll notice there's like Etsy one. Hey, you probably changed that one. Yeah, I did. That's my change. But, and again, Btrfs is really cool. The thing I don't like is how you upgrade it. Because microOS they're like, well, actually, we don't have to do any of that nonsense of like hiding upgrades. We're just going to let you do Zapper, which is basically Yum, right? We're just going to like Yum update the whole thing and then snapshot it. And I'm like, that's the thing we're trying to not do. That was the thing I was trying to get away from, is not doing Yum update on a server. Yeah. I have it backwards? Oh, Yum was a... Right, and then when I reboot, I snapshot, snapshot, run the updates, and then reboot, but that reboot comes from the new snapshot. So I have two snapshots, but I can have multiple snapshots. Again, really cool. I get all of the really good benefits of what like OS tree, because like I could go back in time multiple times, but yeah, I will do always back up your database before you do the migration, right? It's the same thing. We're like, hey, we're gonna snapshot this, we're gonna do our upgrade, we're gonna take a snapshot, we're gonna reboot. This also gets me out of some of the patterns that the other operating systems require, which is reboots. Because I can mutate more of the file system in place and just take snapshots at the point in time that I want it to exist. So that's really, really cool. But again, the reason we built all this was because we kept running into problems of getting in states that we didn't know about. We didn't build the thing and ship it. We just mutated a bunch of stuff in place. And so that confusion and ongoing maintenance and long-term, what state are we in, gets confusing. I do get some of the benefits of rollbacks, and I do get some of the benefits of immediate backup sort of stuff. But the ongoing maintenance isn't the same thing as what I got with the other distros. Was that accurate, would you say? Yeah, exactly. It is not a backup. It is a state and time, a point in time, and then it has its own sort of like overlay-ish thing that it does to let you keep writing, copy and write stuff. Yeah. You still do need proper backups. Do not rely on Btrfs. Just like do not rely on RAID to be a backup. It's not a backup. Please. What is our? I have like. Yes. Okay. Nix. Start. I called it Nix. Nix is literally a PhD thesis that made it to production. It's literally how we got here, right? Like someone wrote this really cool thing, like, what if we could always reproduce everything in the world? Ship it. And like that's how we got here. And it transformed into a package manager. It became an OS, became package manager, does all this stuff. If you look at it, I think it's Nix, SSH. Everything looks really similar until like in this one, if you go one, I think if it's like one directory deeper, there you go, there's the symlinks. We hit them at the root, right? No symlinks here. Oh, actually, they all go into the store. And again, it's just like OS Street where you're not supposed to, you don't go in the store. That's not for you. Store, yeah, sure. Look at those things. And like, I don't like that Nix is starting to make more sense to me of why I would want to use it. I don't like that, especially on something like a laptop or like a desktop that is not a server. That is something that I mutate every day. When I want immediate mutations, I actually want something that is super flexible at letting me put those mutations in place where I'm at and just keep running. And force me to have the good habits of writing flakes and making sure I document everything I installed. Like, that is the power of Nix, is like, you have to do it the right way, otherwise it won't work. The thing that I don't like about Nix is every command I seem to try to run is experimental. Like, everything I try to do is like, yeah, just enable experimental and you'll be good. I'm like, I don't like that usually. I tend to be on the edge of things, but also I need my computer to work, and running experimental things sounds a little risky to me. So Nix is cool, and again, if I sudo touch etc, hello, it's still mutable, right? Nix is not intended to be immutable. It's tended to be reproducible. And that's a big difference on how it is treated, how the file system works, how the packaging works. And so it's a difference. I'm starting to like it a little more, and I don't like that. Yeah, I know. I know it's going to happen. And actually, I'm thinking of doing this laptop because I don't use this laptop very often. So the last one is the one, and I only got 5 minutes for this. So this is Talos. Make Talos start. So Talos, immutability is not the thing Talos does. Immutability is an artifact in how Talos accomplished its goals. I work at Talos now, or at Sidero Labs. I had been using Talos for a long time, even back when I was using CoreOS, because I really liked one thing about it, where Talos has an API for management. There's no shell in Talos. You don't have user accounts. Every single one of these Linux distros that anytime you want to upgrade them, you start by SSHing in. And SSH has a lot of baggage. You need a user account, you need sudoers file, you need keys, you need all this stuff that comes with that to then run a command to execute something on the file system. That is how all of the distros work. Talos doesn't have that, yeah. MicroOS doesn't require it? How does that work? Sure, like you can enable fully automatic, like Flatcar, CoreOS, you can enable fully automatic updates. Yeah. Sure, and that was the default for Flatcar and CoreOS as well. The thing is, those are run by default by having an agent that executes the command. Yes, systemd is on a cron job that says, run updates, right? Like, that's basically how automatic updates happen. And so, yeah, I do agree. They all do have an automated way of doing it. These ways of making the file system safer do make that maybe a little more sure that's going to happen. But Talos is like, we don't want any of that. We literally call an API to do all of the stuff against the system. The problem with that is showing you what Talos looks like before it's actually doing something. If I actually, I think I started the wrong one again. I need the installed one. Because Talos does run in, I didn't build it. Okay, we're just going to do this one. We'll show you. I don't have a way to ls in, or like to exec in and touch a file. But I wanted to show you how that works. So I did something that is really irresponsible. Don't do this. I made a system extension. Talos has a system extensions as well that mounts container images. The difference for us with system extensions is we build them with a version of Talos. So every system extension only works with one version of Talos, and they're signed for that version, and they won't work for another version. So we assure that this thing, you can mount all these system extensions in place. But I made one for SSH. Again, don't do this. But I made an SSH system extension that I can exec into on a Talos node. So if I make Talos SSH, I am now on a Talos node with a shell, which is, again, not intended to be how it works, but I want to show you how this thing works. So I can do, I think it's on host. Again, it looks similar. This one, again, isn't installed, but it's going to have basically the same thing. The thing that Talos, again, does different is, remember that boot sequence that I told you how a system boots? Talos stops at the init ramfs. We don't have a pivot to another boot thing. The entire thing runs in that stage. So the thing that everyone else does of like, oh, here's where your ignition goes, here's where you customize the system, here's where you lay files on disk. No. We only run that piece. So it only runs in memory. And we wrote our own init system for running the API in memory that does all the things we want to do on disk. By making it so that you only go through that API to do anything on disk, I can't clear the screen. Cool. It makes it so that even, oh, I don't have sudo. I think I'm rooting here. Yeah. So if I want to touch host etc hello, we finally did it. Read-only file system. I cannot mutate that file system because of the way, thanks, because of the way that we initialized everything up front. So that piece, you can change the system, but we make assurances that the only changes to the system go through the API, or they're shoved into corners that have their own little mutable areas, right? And so that's how Talos is doing it. We do a very similar thing with, we don't have AB partitions, but there's no buckets. Again, it's an init ramfs. So we write one ramfs, we write another ramfs, we boot back and forth between them. And that's the whole difference. But again, immutability is a Talos feature because of what else we were doing. It's not the goal, where most of the other systems, that was their goal. Let's make it immutable so we can do upgrades in a standard or a more trusted way. That's it. That's the entire talk. So we have, I think, like a couple minutes for questions if there's more. Yeah, right front.
I don't know. I thought the bit about OS tree is interesting. I know they're trying to pivot to a ComposeFS backend for Bootsy. It looks kind of similar. I don't really know much about how it works under the hood. I'm pretty sure they also store the attributes and the exitures like separately and stuff like that. So it's a little cursed like that. But I think what comes with it is like some verity and like integrity guarantees, like with the hashes, which is nice. But yeah, I just wanted to know like your thoughts on that.
Yeah, I did not. I skipped over some of that just for time. DM Verity is a piece of like, let's validate all of these things. Bootsy's doing that. Bottle Rocket does it, and I think that's it right now. But the ComposeFS is like, what if we had this thing that was an overlay, and what if we made it a three-way git merge? It's basically what it does. It's like, oh, we don't just like shove the overlay in one place and then just put it on top. It's like we actually that's exactly how we take the attributes from one file, the file contents from another one, and you could have something else that you're putting in place. Those get merged into your view. That's the ComposeFS. There are limitations around how that works, but basically we're just composing it in a view that from a user's perspective looks like an overlay, but functions different in the kernel. The DM Verity is a piece that's interesting because it has a performance hit. When you're verifying all your reads and writes on a file system, you actually need to use CPU time and you need to use extra memory. But Bootsy's pivoting to that, and that is something that they're trying to get rid of the layering of RPMs. Something I told them was a bad idea 10 years ago. They're like, yeah, actually. What's that? So you did too. Yeah, it was a bad idea. RPM OS tree was a bad idea 10 years ago. They're finally getting rid of it. Thank you for the validation. Yeah.
Great presentation. At home, I run flat car Linux. I've fiddled with the Fedora CoreOS. I did a quick search for Sidero. Lots of resources on GitHub, but it seemed based off of a 2-second Google search. I didn't see anything immediately for Quick Start at Home. What are resources I could look into?
I mean, docs.cedarolabs.com has all the like getting started. Talos only is for Kubernetes. Every other distro that I talked about is either general-ish purpose, like Nix is completely general purpose Linux. The others are usually like container optimized, where it's like, hey, we have a container runtime and no package manager. Like that's container optimized. And so you can just run whatever container you want, but also like the maintenance is on you to like run Docker Compose or something like that. Talos is like, we only do Kubernetes. It's just like, hey, we will get you an etcd endpoints and a Kubernetes API, and you have fun, right? And all the system maintenance should just disappear. And the reason it was built was mostly because people were tired of doing, I have a user at the OS layer, I have SSH keys, and then I have Kubernetes, and I have RBAC, and I have the user, and I'm like, well, what if we just get rid of the stuff below? So Talos literally has no like etc password file. There's no users defined. You don't have to manage those pieces of it. Go ahead, Lee.
Hey, great talk, Justin. I think what I was getting the gist of on the comparison between distros is like, oh, there's different ways of representing file systems in bytes that we can distribute to people, different like bootloader hacks and stuff that you're like, I'm going to point to this disk, I'm going to mount this image, I'm going to overlay this here. On the Nix thing, I think something you're making me realize is that things inside of binaries and like what the linker points to, and Nix's trick of like patch elf, the content of the binary like pointing to something that's hashed, that also feels like something that's part of like an addressable file system to me in this comparison. Do you have any comments on patch elf and how Nix does things? Like I noticed we were showing overlay, we were showing like disks and partitions. Could you like use like LDD or something like on a Nix binary and show it's pointing to a hash on the file system?
I don't think I have the time. I think we're at time, so I won't be able to demo it. But the thing that's really cool about Nix is it extends the OS tree stuff to like, what if every application had its own file system, right? Like that's the thing, the proof of concept of Nix. It's like, hey, actually, it's not just AB boots or 10 different boots. I can have bash on there 10 times if I wanted, and every single one of them works because it knows the tree, but not every Linux binary is compatible with that. And so that's where I think the patch elf comes into play, where it's like, hey, actually, if we need to overload LD preload, we don't want to do that for everything, so we have to do that on the fly for some of these binaries. That's my understanding of it. I could absolutely be wrong. I haven't jumped into Nix yet. But that's like, because they want to do it for everything, you have to add a few more hacks in there to make it work as flexibly as possible, versus the, Kairos, we're just going to download an ISO and mount that as read-only, and then you run it, right? Like that is a different approach of, let's use a tool to make it look the same, and to the binary itself on Nix, it does look the same, but we had to do a little more hammering to get it there.
Another neat note is you can use any Nix binary with the Nix store on any distro.
You can use any binary from the Nix store on any distro. Because, well, yeah, it has all of its compatibility. Yeah, it has a whole chain of dependencies. So, yeah, that makes absolute sense. Right. You can put the Nix store on any distro and use it as a package manager for those binaries. Yeah.
Good.
I'll also be around. We're out of time, right? There's another talk in here, so I don't want to take.
Well, actually, we're heading to lunch.
Oh, we're heading to lunch. Oh, sweet. We can keep going.
Oh, here we go. Okay.
I forgot it was lunch after this. It's lunch on a Sunday. We got all day.
Hey, so I really liked how you pointed out I don't want to be on call on that thing because it's not going to be good for human consumption, because as a recovering SRE, like this talks to me, haven't touched a pager in 10 years, but who knows. What's the story on Talos there? Because you were like, we don't have SSH, and I'm like, well, I think just between us, everybody don't stop listening, but SSH is probably one of the first tools I reach out to when I need to troubleshoot something. So what should I do on Talos?
The API is the most interesting thing of Talos, in my opinion. The immutability, the other pieces of it, I really don't care about. The API is the thing that I want to exist more places. And what do you do? What are you doing when you SSH? In pretty much every case, you're going to get some data. You're going to poke at the system to get data to understand the state of the system. We can do that other ways, right? Like when I really think about what is SSH doing, right? Like I run SSH and it opens a socket file on my local system, opens a network connection, opens a socket over there, and then like pipes a shell, like my keyboard and mouse over to there, out to my display. Like why isn't that just HTTP? Why can't that be another way to get data? And so Talos, I'm not saying it's perfect, I'm not saying it has all this stuff, but we do have some debugging endpoints. Right? Like if you want to go to the API and say, I want a TCP dump and see what's going on there, we have a TCP dump API endpoint. And so you can just go Talos control TCP dump, and it gets the same data you would get from TCP dump running on that host. It does run a TCP dump implemented in Go and just streams the data back to you. Right? There's no reason that my interaction point has to be local socket network, local socket sort of thing. Right? Like we know how web servers work, right? We secure the internet with web services and we send data back and forth through APIs. And so doing that at an API level, I would love to have more debugging tools. And we actually, in the next version, we have a debug container, which is exactly the same thing that like CoreOS did back in the day, where it was like, this is your toolbox, right? At some point, you do need your own tools to run something, and so we have a debug command that will just download an OCI container and put you in the shell, right? Like we can do that. It still goes over the API. It's not SSH, right? It's like, is it like session manager? Like all these proprietary SSH's implementations are kind of just like, we just need data from the box, and I can't get it from logs, so they need to poke at something a little more. So having the API there is just a different way to get the data. And I want more ways that are, easier for people to consume, because LLMs aren't good at shells, right? Like LLMs are great at APIs and specs, and I can give them the API spec and say, cool, get me this data from this spec, and it'll do it for me. But if I tell it go SSH and then like find something for me, I run a bunch of risk of it going off the deep end of running some other command.
Any other questions? Got some hands up.
Yeah, I thought it was interesting about Talos, how you were saying that, in the container environment in Kubernetes, that you don't want to deal with that like bloatware of like users and groups and et cetera. And so I'm really curious, like, how minimal of an image can you make in Talos? Like, what's the bare minimum, and like you can run your apps and still have the API be functional? Like, I'm assuming there's some minimum components needed to make that API still work. So.
When I started, I was like, I'm going to start from scratch. When I started at Cedera, I was like, I'm going to start from scratch, and I've never compiled the Linux kernel this much since college. Fun times in college. Anyway, I compiled Talos, and I was like, let me just like dump the file system. Just tell me what's on here. And I looked at user bin. I'm like, what's on this? And there's a bunch of symlink stuff. I'm like, wait a minute. There was 11 unique binaries on the entire system. 11. I'm like, my Chrome runs more unique binaries than that. And I looked at other file systems for other distros, and there's, thousands and thousands of executables all over the file system, which is one of the things that like make it hard to upgrade and maintain. Like, we don't know what any of this stuff does. We don't know where the CVEs come from. It just takes more time to download it. Remember mini CDs, the 3.5-inch CDs that you used to use for like, business cards, right? Back when business cards were a thing, they would hold like 100 megs, and I could burn all of Talos to a mini CD, and it was just there's other stuff in there. We have kernel modules, we have stuff to run drivers. We designed it to run on bare metal servers. It works in cloud. We do similar things like the OEM drive. We have what's called a platform. Like they all kind of do similar things at the end of the day for that. But there was nothing that I realized you could never strip an Ubuntu or a Red Hat or anything else down enough to say, we're good now, right? Like we took away everything that we don't need. The founder took the other approach. We're like, I'm gonna take the Linux kernel and I'm gonna run the kubelets, was his original attempt. It didn't work because the kubelet's not intended to be run that. He wanted kubelet to be PID 1, and kubelet did everything else. He put the API shim in there just because I do need to debug things. I didn't know when it wasn't working. I didn't know how to fix it after the fact. But that's literally it. It's about 100 lines of Go for an init system. The systemd's like 10,000 lines of C. like it's just we run an API and an init system to run containerd and a kubelet, and that's it. And everything else should be in your container. Not everything works. A lot of bad habits over the years of people expecting that binaries exist on the host. They shell out to things. They run stuff that it's not going to be there. Those things. Talos has been around for 8 years now, I think. We've gained some steam on you should package bash if you need it in your container, right? Like don't make it rely on the host. And so that it's come a long way, but I will say like not everything is there, but we definitely have a lot of users, especially home labbers, that we get a lot of them that were like, K3S is great. Running K3S and initializing it, fantastic experience. The curl to bash, beautiful, right? But then once you go to upgrade Ubuntu, and you're like, oh shoot, how do I make sure K3S is up to date on the same kernel? And all this stuff ends up being not matched, right? And so building one system holistically that says we do one thing and we know what versions we support, we know how to migrate to and from those versions, it just eliminates a lot of the concern, which was, in my opinion, the original goal of how do we make sure updates are fast and easy and mature. And that, like, you have to build a fully stacked system instead of picking and choosing the pieces. We're like 10 minutes over now,
Yeah.
so I don't want to take any other time. So thank you all for coming.
Yeah, let's give Justin a round of applause. The next talk in this room is going to be starting at 1:45, so you are released for lunch. Remember, this is the Systems and Architecture or Systems and Infrastructure track. So you'll see everybody here in just a little bit. Thank you so much.
Okay. Oh, good. Testing 1, 2, 3. Test 1, 2. Parsimonious. Okay, good. I'm not popping my P's. That's good. Yeah, we should be all set then. Test, test. Okay. Sounds good.
Welcome to the System and Infrastructure track at SCaLE 23. If you feel unsafe at any time, please call our safety number posted around the venue. Our next talk is The Tip of the Iceberg, presented by Alex Rasmussen. We will take questions at the end of the presentation. Please welcome Alex.
Good afternoon, everybody. Thank you, Paul, for the introduction. My name is Alex Rasmussen. I'm a freelance data engineer. Over the course of roughly the next 40 minutes, I'll be leading you on a whirlwind tour of the Iceberg table format. So without further ado, let's dive right in. So for the rest of this talk, we'll start by kind of motivating why Iceberg exists. We'll talk about what the inside of an Iceberg table looks like. We'll talk about some of the benefits that Iceberg gives you, and then we'll talk about the hard parts. How do you maintain these tables and keep them happy in production? And what are the rough edges you're likely to encounter? And then we'll conclude by just some thought exercises on how you might decide if Iceberg is worth it for your use case. So if you are used to databases, dealing with object stores for table storage, if you're dealing with them as raw files, is going to be a pretty disappointing experience. If you've done this in the era before table formats like Iceberg, you might have a layout of files that look roughly like this. This is what is colloquially referred to as Hive-style partitioning after the system of the same name. And you'll notice that your files are kind of organized into a tree. And if you're in S3, this is a tree of key prefixes. If you're in HDFS, this is a tree of directories. But regardless, you kind of got this top level that describe your first partition. In this case, we're partitioning by year. You've got your kind of child directories that refer to your second level of partitioning, in this case, months. And then at the end, in kind of the leaves of your partition tree, you have all of your files. And you can kind of use whatever format you'd like in this mode. But more often than not, you're going to see this data stored in a columnar format, probably in Parquet, since it's been sort of the default for a long time. And this layout has a whole lot of problems that you are going to encounter pretty much immediately. The first big one is that there's no really well-defined notion of what a transaction is in this world, and that causes a whole lot of misery. The first thing is, if you're writing to this table and somebody comes along, can you still hear me? I realize I'm popping into my microphone a little bit more than I would like. So you're writing to this table, and you crash in the middle of the write. Well, it's possible that you've just left some data scribbled all over your table that a reader is now going to be able to read. In the database literature, this is what you would call a read uncommitted fault. This happens even if you don't crash, if somebody happens to come around at the wrong time. A lot of engines have tried a bunch of engine-specific, let's call them what they are, hacks to get around this problem, everything from multi-part uploads to Sentinel files that say I'm done, that you have to check before looking at the table. And all of that has just kind of swept the problem under the carpet. It hasn't really actually solved anything. So we don't have transactions. That's a shame. These tables are also really hard to change. And there are two kind of ways that you might want to change the structure of your table. The first is by repartitioning it, changing that partitioning scheme. And since your partitions are so tightly coupled to where those objects are in object storage, or where those files are in your file system, if you want to repartition them, you basically have to rewrite the entire table, because you have to change where those files are and what data is contained in each one. Schema evolution is also complicated, which is a little bit surprising if you think, file formats like Parquet, they've got schemas attached to every file. You know what the schema of a Parquet file is kind of by looking at its headers. So wouldn't it make sense that if you had a whole bunch of them in one place, you know what the schema of that thing is? Well, yes, kind of, right? It turns out that someone can just come along and write whatever Parquet files they want into your table in this world. They can have whatever schema they want. So the only way that you really know what the schema of your table is by looking at every single file in that table one at a time. You can kind of get around this if you have a data catalog that gives you the kind of schema of the table, but you kind of have to trust that that data catalog is right, and that all of your writers are manipulating it in the appropriate way, and that's maybe not always a safe assumption. So this is bad for operators. It's also really bad for query planners and for database engines of all kinds, because the kind of scan planning that you can do in this environment is really primitive. So in that table that I mentioned before, where you've got a directory for year and then every one of those has a directory for months, if you want to select a particular month or a particular range of days, you actually have to structure your query in such a way that you're referring to the year and the month directly. I can't say, give me all records on March 8th. I have to say year equals 2026 and month equals 3 and so on. It gets worse though, because inside of each of those leaf directories where you've got all your data files, you have no idea what data is in each of those files until you look at them. And so if you're a query planner and you're trying to figure out which files to touch as part of a query, you really have to look at least the headers of every single file in the partitions that you're scanning. And when a table gets really big, this gets really, really slow rather quickly. So all of these things together kind of have caused the industry as a whole to shift to the way of thinking that really storing data in this way for tabular data in object stores is just the wrong abstraction. And a lot of big companies that were early adopters of the kind of big data cloud native way of doing things hit this realization at about the same time. And one of them was Netflix. So in 2017, a group of engineers at Netflix began development of the Iceberg table format, and they described it as follows. I'm quoting the spec here. That Iceberg is designed to manage a large, slow-changing collection of files in a distributed file system or key value store as a table. So they set out to be like, well, we're going to solve this problem. They're not the only team that had this realization. At about the same time, a group of engineers at Uber were developing Hoodie, and a group of engineers at Databricks were developing Delta Lake. We won't really have time to talk about Hoodie and Delta Lake in this talk. Suffice to say, they are very similar in some respects and extremely different in others. They're all designed to solve roughly the same set of problems. The reason why I'm focusing on Iceberg here is that in terms of just breadth and depth of industry adoption, Iceberg appears to be kind of pulling ahead. It's got the most mind share. Every single vendor under the sun either is integrating or has integrated with the Iceberg table format at this point. LinkedIn in particular has said publicly that they have more than 10,000 Iceberg tables deployed in production. I've personally worked with clients that have hundreds of terabytes of Iceberg data under management. So it's here, it's relatively mature, and a lot of people are excited about it. And these table formats together have kind of ushered in the era of what they're calling the lakehouse architecture, which is kind of all the nice things about a data warehouse in terms of schemas and transactions and all of that nice stuff, with the scalability and flexibility of a data lake. And we'll talk at the end of the talk about the pros and cons of this approach more broadly. So now we know why Iceberg exists. Let's look a little bit about what an Iceberg table looks like under the hood. So before we go any further, it's important to note Iceberg is not like DuckDB or ClickHouse. There's no Iceberg binary that you can download and run. Iceberg is a specification of a file format, really. It's a specification of a table format. And in that way, it's very similar to like Parquet or JPEG. It describes how stuff is laid out. It describes how you write that stuff and how you mutate it. But there are many different implementations of the Iceberg spec that exist. I would argue that if you're looking for a reference implementation of the Iceberg spec, you're going to be looking at the Iceberg client for Spark. It's the one that Netflix was working on the most heavily in first, and it's by far the most mature in terms of what features it's got implemented. There are also several versions of the Iceberg spec. It's a spec that's continuously evolving. We're going to be talking about version 3 of the specification here, just because it's the one that's kind of the mature one as of the time that I'm giving this talk. So, what does an Iceberg table look like? So the kind of lowest level and most primitive thing that you have in an Iceberg table are data files. As the name might imply, data files are where all of your data lives. It's where all of the rows that comprise your table are stored. It's important to note that these data files, and in fact all files in an Iceberg table, are immutable. This means that once you write them, you cannot change them. And a data file is storing data in a single partition but a partition may contain many data files, and there may be many partitions in a table. So that kind of begs the question, well, if you can't change data files, then how do you update rows in a table? It turns out there are two ways you can do this. The first is what's called copy on write, where if you want to make a change to a data file, you read that data file, you do any changes you need to do, and you write out a copy. Second way you can do this is what's called merge on read, where you leave that original data file alone, but you write these two kind of auxiliary files attached to it, one of which is called a delete file. It's just a very concise way of saying this data file has the following rows deleted from it. And then you add another data file that describes the rows that you add. So if you want to update a row, you write a delete file deleting the row, and you write a new data file that contains the row's new version. These two write methods have their respective trade-offs. Copy on write, it turns out to be a lot faster for readers because you only have to read one file, and you don't have to do any kind of processing to stitch them together. That's just what the data is. On the other hand, if you want to change one record in a data file, you've got to copy the whole thing. So it turns out that writers are a lot slower that way. On the other hand, merge on read, a lot faster for writers because you're only writing those two sidecar files, but it's slower for readers because you have to read all three of those files and then kind of logically stitch them together to figure out what the actual state of that file is at any given time. So you've got all these data files and delete files sitting around in your object store. How do you find them? Well, you organize them into manifests, and you store those manifests in these things called manifest files. And a manifest file is really just an avro file with a row for every data file in the manifest. And each one of those rows has the path to the file, but it also has a bunch of information about the file, like what partition the file is in, and a lot of statistics about what the maximum and minimum values for its columns are, and how many rows it contains, and all kinds of other stuff like that. And that's really useful if you're a query planner, because you can actually look at the manifest and figure out which files in that manifest you need to look at without actually looking at the individual files themselves. So it speeds that up a whole lot. Russell Spitzer gave a really deep dive talk at the CMU Databases seminar series last year about how scan planning works for Iceberg and Spark. I would encourage you to check that talk out. He goes really, really deep into how this works. And I've put a link up there on screen. So you've got these manifest files sitting around in object storage. Well, how do you find those? Well, what you do is you organize those together into a manifest list. And a manifest list looks a lot like a manifest file. It's an avro file, except every row of this file doesn't refer to a data file, it refers to a manifest file. And it also has metadata, but that metadata just describes all of the data in a given manifest. So it's got minimum and maximum values and counts and all of that other stuff. And this is just also there for the benefit of the planner so that it can look at entire manifests at a time and go, oh yeah, I don't actually need to look at anything inside of this manifest when I'm running my query. So you've got your manifest list that points to your manifest files, that point to your data files. What we're going to do is we're going to take all that stuff and we're going to wrap it in a thing called a snapshot. And a snapshot is really just the state of the table at a particular point in time. And all that is concretely is a bunch of metadata plus a pointer to the manifest list. And that snapshot is kind of the bread and butter thing that represents what you're querying when you query an Iceberg table. You are querying a snapshot of that table. Now, snapshot information, like everything else, is immutable. So every time you write to an Iceberg table, you're generating a new snapshot. Well, how do I know where all of the snapshots are and which snapshot is the right one to be querying right now? Well, we roll that up into the kind of top level thing on the tree of files in Iceberg, and that's the metadata file. And the metadata file has a lot of information that's useful about the table, like its schema, metadata about partitioning, table properties, and that sort of thing. But it also contains a complete history of snapshots and a pointer to which snapshot is the current one. So that metadata file represents kind of the current state of the table. But whenever you make a write to an Iceberg table, you're generating a new metadata file. So how do I know which metadata file is the right one? Well, that's the catalog's job. So the catalog has effectively a pointer, and that pointer says, well, my table is a pointer to this particular metadata file that sits on object storage right now. And if I want to change the table, I got to write all these new files, and then I got to repoint the catalog at the new metadata file. So let's take a look at an example of how that might look. Let's suppose that you have an Iceberg table that looks schematically something like this. You've got some manifest files with a manifest list pointing to all of them, and then you've got your metadata file up at the top with snapshot 0 pointing to that manifest list, and you want to do a write. Well, the first thing you do is you figure out which manifest files you need to change. You make your new data files and your new delete files, as the case may be, and you write some new manifest files, and maybe you throw the old manifest files away, and you take all of those new manifest files that make up the table, and you make a new manifest list pointing to all of those files. And then you call this thing snapshot1. Then you make a new metadata file, and that metadata file says, okay, I've got two snapshots now, snapshot 0 and snapshot 1. Snapshot 1 is the most recent one. Now, this is where the immutability aspect becomes important, because you can see that if, let's say, like I was going and scribbling on the contents of manifest list M0 or M1, for instance, that I would have destroyed information about what snapshot 0 actually looked like. And that becomes important for a lot of other kind of more fancy use cases that we're going to see here in a couple of minutes. So I've got my new metadata file. The last thing I need to do is update the catalog from pointing to the old metadata file to pointing to the new one. And when I do that switchover, I'm done. And my write has now effectively committed. And this is kind of the key hinge upon which all transactional stuff all of that will derive from that one kind of simple repoint of that pointer from one metadata file to the other. So that's roughly how an Iceberg table works. So what benefits do you get from your Iceberg table that you didn't have with all of your raw files sitting around on disk? Well, the first thing is that you get transactions. And if we want to be really precise, and we were talking about transactions, we got to talk about ACID. So ACID, it's an acronym. It stands for Atomicity, Consistency, Isolation, and Durability. Atomicity basically says that all of the changes that you're making as part of a transaction happen all at once in a single indivisible unit. A write doesn't kind of part way happen. Consistency says that the table moves from one valid state to another, so there's no way that a write can leave the table in a corrupted state. Isolation effectively says that if you have multiple transactions happening at the same time, they result in a final state that's equivalent to if they had run one at a time in some order, right? So there's going to be no weird stuff happening as a result of interleaving transactions on this table. Finally, durability just says once a transaction happens, it does not unhappen even if you crash. So how do we guarantee these properties in Iceberg? Well, the atomicity property is satisfied by that atomic swap from one metadata file to the other. And it's really the catalog's job to assume, or rather to enforce, that that swap is atomic. The consistency bit, well, while you're writing that new snapshot, readers don't see the new snapshot until you commit. And if you fail in the middle of that process, you've left some files lying around, but the table's still fine. Like in that situation, if I had crashed in the middle of creating snapshot 1, snapshot 0 is still chilling. It's still cool. The isolation property you satisfy by applying these snapshots in some total order. The catalog will basically move from one snapshot to the next, to the next, to the next in some well-defined order that all readers see. And for durability, I mean, look, you're storing this stuff in S3. It's as durable as S3 is. I'm pretty sure that S3 is going to outlast all of us. So I think that property is pretty well satisfied. So if we want to get really pedantic about it, the kind of isolation guarantee that Iceberg gives you is what's called serializable isolation, which means that the transactions appear to have occurred in some total order that all readers see. So if I'm reader A and reader B, reader A is not going to see snapshot 0 appearing before snapshot 1, Reader B will see snapshot 1 appearing before, snapshot 0 appearing after snapshot 1. They'll all happen in the same order. The way that it handles concurrency is through what's called optimistic concurrency control. This means that if multiple writers are trying to write to the table at the same time, one of them will win and all of the others will lose. And they will either have to back off and retry or they'll have to abort. And as we'll see, this can be kind of tricky in production. We'll talk about that in a minute. So we have transactions, that's awesome. Schema evolution, recall that that was very difficult to do well in our previous world. Now schema evolution is effectively instant. The way that Iceberg does this is really interesting. So when Iceberg defines a schema, it defines schemas referring to fields by a numeric ID. So it doesn't say, I have columns A, B, C, D, and E. It's I have columns with IDs 1, 2, 3, 4, and 5. And this is really useful because if, let's say, for example, I drop column A, and then later I create a new column whose name is also A, but is logically a different thing, happens more often than you'd think, then there's no ambiguity about whether I'm talking about past A or present A when I'm referring to a particular column, because everything's referring to them by an integer ID, and the field's name is just a property. It's not an identifier. This means that if I want to change the schema, really all I have to do is write a new set of schema metadata to the metadata file and commit the new metadata file, and now my schema has changed. And evolution just sort of happens as a side effect of that. There's a little bit of metadata that you have to store with your data files so that if they're referring to these fields by name, that you can map the names to IDs, but that's a very minor detail. So schema evolution, I think we've got that under control. The table knows what its schema is, and it's very easy to mutate it. Repartitioning, which was a nightmare before, is instant-ish. So what do I mean by that? So in an Iceberg table, what partition a data file is in has nothing to do with where that data file is in storage. In fact, you can even lay out your data files across a bunch of different randomized prefixes, and Iceberg does do this on S3, to improve the number of reads that you can do at the same time, because S3 rate limits reads based on prefix. So it gets better though. Not only does the partition that a data file is in have nothing to do with where the data file is, it actually doesn't have to have anything to do with the actual data in the data file itself, at least not directly. Instead, a data file's partition is described by a versioned function called a partition spec that's applied to the data file's data. So if you want to figure out what partition a data file is in, you apply this function to its data, and that gives you back a partition, which is effectively just a tuple of values. I've given a very truncated example because these things are very difficult to put in a way that will fit on a slide and still be readable. But in this sort of snippet, we've declared a partition column called ts_day, and it's derived by taking the field with ID 1000 and truncating it down to the nearest day. So if you wanted to change the table's partitioning scheme, for instance, if you wanted to partition by month instead of by day because your partitions were getting too numerous, the only thing that you would need to do to change the partitioning in the table, at least lazily speaking, is to make a new version of the partition spec that describes a new function and commit that change to the metadata file. None of your data has to change immediately as the result of that. And any data that you write after this will be written with respect to that new partitioning scheme. Now, this does mean that you still have the problem that if you want to sort of optimize your table so that everything is in that new partitioning scheme, you have to do a rewrite. But the thing that's nice about this is that you don't have to do the rewrite immediately. You can wait, and you can even be selective about what you rewrite. For instance, you might decide that for performance purposes, you really want the most recent year of data in your table to be partitioned in a particular way. But the rest of your data can stay in the legacy partitioning scheme forever because you're hardly ever going to read it. And when you do, you're okay with that being a little bit slower or kind of more suboptimal. And this kind of gives you a lot of power in terms of tuning that sort of cost-performance trade-off, especially once your tables start getting just enormously huge. So these are the core benefits of Iceberg, but they are by no means the only things that you can do with Iceberg. And in fact, a lot of the kind of cool stuff that you can do with Iceberg tables is a consequence of the fact that it consists solely of this sequence of snapshots at a point in time. You can do all kinds of stuff with this. The first cool thing you can do with it is time travel. So you can actually query the table as of any point in time or in kind of snapshot history that you still have stored. If you query as of a particular snapshot, it will just query that particular snapshot ID's metadata file. If you want to query as of a particular time, the planner is expected to be smart enough to look at the snapshot history, find the one that would have been current as of that time, and query that. So that's cool, gives you a lot of ability to kind of look back in history and see what changed. You can, build change log tables and stuff like that off of this too, which is kind of neat. The other thing that you can do with this is disaster recovery. So if somebody scribbles all over your table, instead of, them's the breaks and you have to go and fix it manually, you can just decide to tell the Iceberg table, hey, the snapshot that you had back in the past, that's the current snapshot now. And you can do that as of a snapshot ID or as of a time. And this does a lot to kind of pull you out of the fire if you happen to make a bad write to a table. You can also start to treat this snapshot history kind of, sort of, a little bit like Git. So like in Git, snapshots can be tagged. They can have names. And you can define a branch, which is really just kind of like a mutable tag that moves forward as writes to the branch commit. And that gives you a lot of fun things that you can do. Here's an example. Let's suppose that you're on your main branch of your table, and you decide that you want to make some changes, but you're not sure that you want to commit those changes to prod just yet. So you create a dev branch that starts at the latest snapshot on main, and then you do some writes to it. And while you're doing these writes, notice that anyone that's querying that main branch still sees snapshot 3. So you're not doing anything to mess with them at all. And you can go in and validate, in this case, snapshot 5, and make sure it looks good. And if it does look good, then you can effectively stitch dev and main's histories together with what's called a fast forward. Now, the big difference between this and Git is that there's really no well-defined notion of a merge here. So if main happened to have another commit that was a kind of a child of snapshot 3, you wouldn't be able to merge dev into it. That limits somewhat what you can do with this, but the thing that's really nice is that this kind of enables a pattern that's becoming known as write, audit, publish, where instead of writing directly to the table, you write to a branch, validate the branch, and then effectively commit the branch forward into the main, which lets you do a whole lot of high-level semantic checks before you actually make this visible to readers, which can improve just the overall data quality of your system by quite a lot. So as I alluded to earlier, not all is sunshine and kittens. There are things that you need to be able to do to keep these tables healthy over time in prod, and if you don't, you will regret it. Without maintenance, your performance of your Iceberg tables is going to degrade, and the cost of storing these Iceberg tables is going to go up. And there are some ways that this happens. The first I like to call snapshot bloat. If you keep every single snapshot that you do, and you do dozens of writes to a table a day, you will end up with thousands and thousands and thousands of snapshots. And every time you make a new metadata file, you will have to read the entire history of the universe, add one snapshot to it, and write the entire history of the universe back out. In some cases, this is what you want. In most cases, it isn't. So what you want to do is you want to kind of garbage collect old snapshots after a period of time. There's a batch operation that will do this. It's called snapshot expiration. You can control what snapshots are expired with two different parameters, kind of the maximum age of a snapshot and the maximum number of snapshots that you want to keep. Those two things are important because, you know, if you don't write to the table for a long time, you don't want all snapshots to fall off the face of the earth. You really only want the ones that you don't want to keep around anymore. Those parameters, that maximum age and the maximum number to keep, can be set on the table level, but they can also be overridden on a branch or tag basis. And this operation, effectively, it's like any other transactional operation in Iceberg. It creates a new metadata file. It doesn't actually create any new manifest lists or manifests or anything like that. It's just an update to the metadata, which makes it quite fast. Another problem that you'll find is if you have writes that abort for any reason, they will kind of leave bits and pieces of partially committed snapshots lying around. Now, as I mentioned, that doesn't actually hurt your table at all because the table is guaranteed to consistently move from one valid state to the next, but it does start to increase your storage costs over time, especially if you do a really, really, really big write that fails 95% of the way through. So every once in a while, you need to go through and garbage collect all of your orphaned files. This process effectively involves enumerating all of the objects in the bucket and comparing that with kind of the closure of all file paths from the metadata file on down, and just getting rid of files that aren't on the list of valid files in the table. Then finally, you are also victim to a very common problem that is not unique to Iceberg called the small files problem. Small files can be caused by a bunch of different things. You might have a Spark job with way, way, way too many tasks that's writing a bunch of teeny tiny files when it really should be writing a few big ones. You could be doing a lot of merge on read updates, in which case you have a lot of delete files and a lot of those tiny little sidecar data files added on. You can be doing a lot of small appends or a lot of small deletes. You might also just have partitioned your table poorly, you know, by something that's really high cardinality, so you've got way too many partitions, and so every time you write, that gets spread across all your partitions and your resulting files are quite small. This can be solved, though. It's solved through a process called compaction. And compaction just looks one partition at a time, takes all of the data and delete files that exist in that partition, and it kind of tries to squeeze them down into as few files as it can. That has a ton of different parameters that control how aggressive you want to be about the squeezing down and how many partitions you try to do at a time and how often you checkpoint this compaction process by committing a new snapshot with the compressed partitions replacing the uncompressed ones, but that's something that you're definitely going to want to be very mindful of doing as your table continues. So those are your big maintenance challenges with Iceberg. There are also a few rough edges with the format that you're bound to encounter if you deploy this at any kind of scale. The first that I alluded to earlier is that optimistic concurrency control really does present kind of a challenge in production because you kind of have to operate in a world where at most one thing is writing to your table at any given time most of the time. And even if you're really, really careful about doing that with the kind of the real work that you're trying to do to the table, you also have to worry about the maintenance work and the real work conflicting with each other. So for instance, you might have a compactor that fires on a regular schedule that takes long enough that it collides with a normal write, and that write may have to abort because the compaction gets in its way. This is a big problem. It's something that the Iceberg folks are very well aware of. There's been a lot of work going on in the context of the Iceberg REST API, which we don't really have time to cover in any detail here, around something called server-side deconfliction, which is the idea that the catalog really should be trying its best to merge multiple transactions that have no possibility of conflicting with one another together in a way that allows both of them to commit. But that's very much like an ongoing problem. So all the maintenance stuff that I talked about, Iceberg is a table format. you basically have to rely on your query engine or some other thing to do that maintenance for you. There are many, many vendors out there in the world that will try to sell you a thing that will do automatic maintenance on your Iceberg tables, and they will probably charge you an arm and a leg for it. S3 tables being one of many, many examples of this. If I had to give a piece of very broad advice, I would say if you're just starting out with Iceberg, your best bet is probably just to run Spark jobs on a cron to do some of these maintenance jobs. Even at the scale of dozens of tables, it's really not that much maintenance burden, and a lot of these systems don't expose all of the knobs that you can tune, that if you were to just call a Spark procedure yourself, that you'd be able to go and dial that in. And sometimes from an operational perspective, that can make a lot of difference. Finally, Iceberg's been around for a little while, but it's only just started to kind of go parabolic in terms of adoption. So engine support is still a little bit uneven. Spark has really good Iceberg support. Trino has really good Iceberg support. A lot of the rest of the stuff, it's a little bit hit or miss. Some engines can only read Iceberg tables but not write them. Some draw a weird distinction between what they call internal Iceberg tables and external ones. As best as I can tell, that really just means that the internal one is their format that's kind of pretending to be an Iceberg table from an API perspective, whereas the external ones are written according to the actual spec. There's also stuff that you're used to from databases like multi-table transactions. Catalog support for that is really, really thin. I think Dremio might be the only one that's really got it fully fleshed out right now, although Polaris is also making great strides there. If you want the most exhaustive comparison of Iceberg feature matrix across engines in the history of time, a company called Olake publishes this comprehensive breakdown. They go into just incredible detail on what each engine can and can't do, and they're keeping this up to date, which is awesome. So in conclusion, we talked about how table formats ushered in this idea of the data lakehouse, right? All the nice things about the data warehouse and all the nice things about the data lake put together. And based on the last few slides, you might think that the data lakehouse is maybe selling you a little bit of a bill of goods, right? That there's a lot here that you have to do yourself, right? And that's kind of true, right? I think just like everything else in our field, it's all about trade-offs. You gain some things and you lose some things, right? So what do you gain? In this kind of lakehouse setup where your storage is completely decoupled from your query engine, you gain a lot of flexibility. You can have a lot of different kinds of query engines that are operating on the same data stored in the same Iceberg tables. And for some places, particularly, people who are dealing with multimodal stuff or people who are dealing with, batch and streaming workloads working together, this has a lot of really nice benefits because you can sort of pick best of breed query engines for each of your different tasks, and as long as they support Iceberg, you can go off of a common carry. There are even folks that are crazy enough to do things like replace Kafka's storage tier with Iceberg and just have the Kafka API sitting in front of it. But you gain a lot of flexibility. Also, as I alluded to earlier, there's this multimodal thing here where if you want to have video and images and tabular data all sitting in one place, having that all sitting in your S3 bucket and being able to query that is, nice if your query engine can do that sort of thing. There's a sort of big selling point that the lakehouse vendors give you talking about vendor lock-in and how Iceberg prevents you from being locked into a vendor, or how table formats generally prevent you from being locked into a vendor. That's technically true. I think that if you look at the kind of way things are going, a lot of companies are tending to integrate their own solutions vertically and call the resulting thing a lakehouse if the storage engine is, or the storage tier is in S3. Looking at you, Databricks, Delta Lake is awesome, but you basically have to be in Databricks' ecosystem to be able to use it effectively. I think really, and you're also you're gonna see better integration with a given piece of open source software at the company who's sponsoring all of the people developing that thing. Tabular got bought, and immediately, everything started to kind of look a lot better for the folks that were acquiring Tabular. So we talk about what you gain. What do you lose? Well, there's a lot to be said about working inside of a system where the query engine, the data catalog, and the storage engine have all been co-designed and co-optimized for one another. You can get a lot of performance improvements off of that. You can get a lot of just operational simplicity off of that because your system is very vertically integrated and nice and cohesive. Is that worth it? Well, you know, you also do have to factor in, like, if you're in the Snowflake ecosystem, there's a lot of stuff that Snowflake does very well for you that you'd have to patch together from a bunch of different open source tools if you were doing it the Lakehouse way. But you also kind of have to look at that Snowflake bill every month and realize that, like, it's going to take you an awful lot of work to migrate off of that platform. And really, like, is it worth it? It really just, it depends on where your business is. It depends on what your goals are. It depends on where you're going. If you want to know more about that, I am available to ask questions too. So wrapping up, we kind of established that raw files on object storage is the wrong abstraction for tabular data and that something new was needed. And Iceberg, I think, fits that bill. It makes the tables that sit in your data lake a whole lot easier to reason about, a whole lot easier to evolve, and a whole lot easier to test. However, you know, it is not without its trade-offs. You need to do periodic maintenance on these things. Doing operations on it can be tricky at scale. And for some of these query engines, adoption for Iceberg is still in early days, so you're kind of going to have to deal with a little bit of rough corners. Overall, though, if the situation that you're in right now is you've got a bunch of files scribbled all over a data lake, man, you really should consider upgrading to a data lakehouse. Your heartburn will thank you. And with that, thank you very much for your time and attention. I am here to take questions. I am a freelance data engineer. I help startup companies build, manage, and scale their data infrastructure. If that sounds like something you would be interested in talking more about, please feel free to use that QR code or just email me directly. And that's it. I'll take questions.
Okay, are there any questions? Oh,
Hi, thank you very much for the talk. It was brilliant. Can you give us some examples of the types of data that you'd see being stored in Iceberg?
Totally. The biggest one, honestly, is event data, like high volume event data, particularly if you're looking for a place to store data archivally, right? A use case that I see a lot these days is that folks will keep the kind of hot tier of their event data for like the most recent 30 or 60 days in an engine like ClickHouse and be able to do kind of real-time OLAP on that. And then the rest of it, they'll tier down to Iceberg and just append it down as it kind of falls off the edge of the world with ClickHouse. And then if they need to do more archival stuff or they need to do like disaster recovery or backfill, they'll go down to Iceberg for that. I've also seen a lot of folks that are doing CDC off of their OLTP databases directly into Iceberg and then using that to have multiple query engines kind of chew on it depending on the size of the problem that they're trying to solve. So you might have some things that are using DuckDB and then other stuff that's firing up a whole Spark cluster off of that same tabular data. Thanks.
okay. There's a question.
Hi, nice talk. My question is around the like the offloading data from CDC data from like a lot of like the BGM connector go to Kafka, and then that's kind of one of the best practices.
Sure.
One of the things we faced with Iceberg sync connector, like they don't support deletes and updates. So we end up writing to a raw table, like everything, and then we run a Spark job to do the maintenance. So
yeah, so that's interesting. So what you're talking about is kind of the way that the kind of best practices, quote unquote, way that CDC down to Iceberg is done. The idea there being that you're taking the kind of raw insert, update, and delete statements off of, let's say, Debezium, and you're appending those into a file, and then you're sort of tailing that list of appends to do the merge and apply. That, honestly, I think is driven more by trying to make sure that you keep up with the speed of the data coming out of Debezium, right? So one of the things, I didn't really get into this in the talk, but one of the things that's interesting about Iceberg snapshots is that you can have different kinds, right? So if you have a snapshot that only appends data to a table and doesn't do any updates or deletes, you can actually ask the table, give me all of the stuff that's been appended to the table since the last time I checked, and use that as the input to a merge into operation to like update the actual sort of materialized view of your table in Iceberg. And the thing that's really nice about that is that especially if you have a table that's being written to at like an absolutely blistering rate of speed, you really don't want that Debezium topic to get huge. So better to just offload it all into that append only, like that append snapshot structure, and then come back periodically and materialize it. The other thing that's nice about that is that if you're really, really clever, you can create a view on top of that materialized view and the changelog stream that will allow you to either say, well, look, I want this query to be pretty fast, so I'm only going to query the materialized thing. But if I want it to be really up to date, I can query the materialized thing and then like actually just stitch together the rest of the delta at query time and get something that's much more up to date with the current state of the table that way. And you can kind of choose which one of those you do. And funnily enough, if you look at the internals of like a Hoodie or a Delta Lake, it looks very similar to this, where you've got this sort of change log of things coming in that periodically gets snapshotted into kind of the materialized view of the universe.
Yeah, I think the idea is like use materialized view. Currently what we do when we write, we use the merge on write. On the read side, we use the copy so that the Spark, both writers and readers have the best performance. But
right.
I'll look into the materialized view solution. Thank you.
Cool. Thank you.
Okay, a question in the back.
Do you have any suggestions of would a lake house be overkill just for backfill, or would I be better off just using like Parquet with DuckDB? Because right now I'm looking at the use case of we have a backfill issue that we're trying to fill in like lost data on like a daily basis, maybe for on the realm of like an hour or maybe 15 minutes of lost data.
I see. I think it depends. I think the nice thing about storing this data in Iceberg is that it's very easy to pinpoint the exact data that needs to be backfilled by querying it, and that query is going to be reasonably efficient, assuming that you've partitioned the table the right way. I think the problem that I've always seen with, a bunch of files, just Parquet files that you query with DuckDB, is that you're running into some of the same problems that I was talking about in sort of the quote-unquote old way of doing things, right? Where if you need to know which Parquet files to scan to do that backfill, you have to look at the metadata for every single one of those Parquet files to figure out which ones contain the data that you want. And of course, you can be clever about that if you've laid your files out in a particular way, but sometimes people are and sometimes they aren't. I've particularly seen like folks that really struggle with trying to backfill off of, like, let's say you have an S3 sync connector from Kafka, right? That sync connector is just going to write a file per topic partition that's just named by the offset of the first record in that file. And it's impossible to really tell at a glance which files to scan. So I think in those situations, like, again, though, it depends. I think you have to populate that Iceberg table somehow. If the backfill is a very occasional operation, it might be better for you to save the cost of doing that query for the few, like, handful of times that you need to do it, and have that common mode write path be really, really straightforward and simple. Does that make sense?
Yeah, I have another follow-up question. Have you seen anybody do anything like crazy, like partition down to the hour at the folder level? Is that like overkill as well?
So I have. Or rather, I've seen high cardinality partitions in Iceberg for sure. It can be done. I think really the question is, how big are your partitions, right? Because there's a trade-off between being selective about what you scan and having the individual partitions be large enough that your query engine can actually chew on them and you're not spending most of your time opening and closing files. So I think Could you partition hourly? Sure. If you're getting in tens of gigabytes of data per hour and you're partitioning by hour, that makes a lot of sense. You'll end up creating some pretty big files that way. Your query engine can chew through it. You can probably cluster those partitions with like something that speeds that up a little bit, Z ordering or something along those lines. But like, if you're partitioning by hour and you get a couple megabytes of data an hour, then probably not. You'd want to do that by the day. I think the thing that's really nice, though, I'll say about Iceberg's partitioning spec is that you're allowed to get that wrong with very little penalty, right? So for instance, suppose you thought initially, oh, I'll partition this by hour. Later on, you're like, oh, these partitions are numerous and very small, and I need to get rid of them. Well, you can change the partitioning spec to partition by day or by month, and then just lazily rewrite your partitions one at a time through compaction to make them larger and less numerous. And you don't have to talk about like, well, I'm going to have to stop the universe to rewrite this entire table because I got my partitioning wrong the first time.
Okay. Yeah, because right now we're just focusing on backfill because we have our sort of live hot data is in a time series database in Influx, and so we aren't really looking at having a lake house for doing OLAP operations on.
Sure thing. Sure thing.
Thanks.
No problem.
Okay, any further questions? Well, in that case, thank you, Alex, for your presentation.
Great.
And please stick around for the keynote address at 3 p.m. in the other building at Ballroom DE. Thank you.
Great. Thanks, folks.